We all know gravity. It's the force that keeps our feet firmly on the ground. It holds the Earth in orbit around the Sun. Isaac Newton described it beautifully with his laws. Later, Albert Einstein gave us an even deeper picture. He showed gravity as the warping of space-time itself. Massive objects create curves in space-time. Other objects follow these curves. But what if this isn't the whole story? What if gravity is something even more fundamental, or perhaps less fundamental? What if it emerges from something else entirely? Imagine a flock of birds. Each bird follows simple rules, yet together they create complex, beautiful patterns in the sky. No single bird plans the flock's dance. The pattern emerges from their collective behavior. This is an emergent phenomenon. Think about temperature. It arises from the average motion of countless tiny particles. You can't talk about the temperature of a single atom. Could gravity be like that? Could it be an illusion, a macroscopic effect born from the microscopic world? This is a mind-bending idea. Now let's talk about entropy. You've probably heard of it. It's often described as a measure of disorder or randomness. The universe, as a whole, loves to increase its entropy. Think of a tidy room. It takes effort to keep it neat. Left alone, it tends to get messy. That's entropy at work. An ice cube melts in a warm room. The ordered structure of ice gives way to the more disordered arrangement of liquid water. This natural tendency towards greater disorder is a powerful driver in the cosmos. So, what's the connection? Some physicists propose a radical idea. They suggest gravity isn't a fundamental force like electromagnetism. Instead, gravity might emerge from the universe's relentless drive towards higher entropy. It's like gravity is a byproduct of thermodynamics. This is a profound shift in perspective. It means the force that shapes galaxies and holds stars together might be intimately linked to the same principle that describes why your coffee cools down. A truly cosmic connection waiting to be fully understood by us. The story of emergent gravity gained serious attention in 1995. Physicist Ted Jacobson made a stunning connection. He showed that Einstein's equations of general relativity could be derived from the principles of thermodynamics. Imagine that. The laws describing how gravity bends space-time. These laws could arise from the study of heat and entropy. Jacobson considered a tiny patch of a causal horizon. This is a boundary beyond which we can't see. He found that the relationship between heat, entropy, and temperature near this horizon mirrored Einstein's equations. Jacobson's work was a revelation. It suggested space-time itself behaves like a thermodynamic system. When matter and energy cross a horizon, the entropy changes. Space-time, it seems, must readjust itself to accommodate this change. This readjustment is what we perceive as gravity. It's as if space-time resists being put into a less probable, lower entropy state. The universe is always trying to maximize its options. Gravity, in this view, is the universe's way of ensuring matter and energy arrange themselves to uphold this fundamental tendency. It's a deep and subtle dance. Then, in 2010, Erik Verlinde took these ideas even further. He proposed that gravity is an entropic force. What does that mean? Think of a rubber band. When you stretch it, it pulls back. This isn't because of some fundamental rubber band force. It's because the stretch state has fewer possible molecular arrangements. It has lower entropy. The rubber band pulls back to reach a state with more arrangements, higher entropy. Verlinde suggested gravity works in a similar way. It's a statistical effect. Verlinde's theory draws on something called the holographic principle. This principle suggests all the information in a volume of space can be encoded on its boundary, like a hologram. He argued that when a piece of matter moves, it changes the amount of information, or entropy, on a nearby holographic screen. The system then tries to maximize its entropy. This tendency manifests as a force, and that force, Verlinde proposed, is what we call gravity. So, here's the big question. If gravity is linked to entropy, why does it pull things together? Why doesn't it push them apart? After all, spreading things out usually increases disorder, right? Think of a gas. If you release it into a larger container, it expands. The gas particles spread out to fill the available space. This is a state of higher entropy. They don't huddle together in one corner. So why do masses, under the influence of entropic gravity, attract each other? It seems counterintuitive at first glance. The key lies in how mass affects the available information or states of the system. Imagine two objects in space. When they are far apart, the information associated with their positions and the surrounding space-time is distributed in a certain way. However, according to these theories, the presence of mass actually reduces the entropy in its immediate vicinity, or it creates an entropic shadow. The system as a whole wants to maximize its total entropy. Bringing the masses together counterintuitively can lead to a greater overall increase in entropy for the entire system. Let's use an analogy, though all analogies are imperfect. Think of having many small disorganized piles of Lego bricks, high entropy. If you bring those piles together to build one large, complex structure, like bringing masses together, you might think you're creating order. But in doing so, you might be freeing up the space those small piles occupied, allowing for even more disorganization, higher entropy in the surrounding room or system. Or perhaps the combined system has access to new states. The specific mechanism is complex, but the idea is that attraction between masses is the path to maximizing the total entropy of the universe. Black holes are the ultimate illustration of this connection. A black hole is a region of space-time where gravity is so strong nothing can escape, not even light. According to Jacob Bekenstein and Stephen Hawking, black holes have enormous entropy. This entropy is proportional to the area of the event horizon, the point of no return. The more mass a black hole swallows, the larger its event horizon becomes, and the greater its entropy. Gravity pulls matter into a black hole, increasing the black hole's entropy. This aligns perfectly with the idea of gravity as an entropic force, driving systems towards states of higher entropy. These ideas about emergent gravity are not just theoretical curiosities. They could have profound implications for cosmology. For example, some scientists wonder if entropic gravity could help explain mysterious cosmic phenomena. Think about dark matter. We can't see it, but its gravitational effects are undeniable. It shapes galaxies and galaxy clusters. Could dark matter be an illusion? Perhaps it's a manifestation of how entropic gravity behaves differently on galactic scales than Einstein's theory predicts. This is a tantalizing possibility. And then there's dark energy. This is an even stranger phenomenon. It's causing the expansion of the universe to accelerate. We have no clear idea what dark energy is. Some researchers explore whether entropic forces related to the information content of the universe could be responsible for this cosmic acceleration. If gravity emerges from thermodynamics, then perhaps the large-scale structure and evolution of the cosmos are deeply tied to these entropic principles. It's a new lens through which to view the universe's grandest mysteries. However, it's important to say that emergent gravity theories are still developing. They are not yet part of mainstream physics. While they offer elegant explanations for some aspects of gravity, they also face significant challenges. One major hurdle is making unique testable predictions. Predictions that differ from those of general relativity and can be verified by experiment or observation. Science progresses through such tests. Without them, a theory remains speculative, no matter how beautiful it might seem to us. The quest to understand gravity continues, from Newton's falling apple to Einstein's curved spacetime, and now to these ideas of emergent entropic forces. Each step has revealed a deeper, more intricate universe, whether gravity is truly fundamental or an emergent property linked to entropy. The pursuit of this knowledge is a testament to human curiosity. It's part of our cosmic journey. We look up at the stars and we ask why.